Hello, thanks for joining us on the Space Nuts podcast. My name is Andrew Dunkley, your host. Great to have your company again. Thanks for joining us. This is episode 316. We've got a lot to talk about today. If you were born on June the 29th and had a birthday the other day, congratulations. You had the shortest birthday in history. We'll tell you why. We're also going to answer a bunch of questions today. We usually do the Q&A version of the show every fifth episode, but which was supposed to be last week. We forgot. But we will do that today. And we've got questions about the Earth's moon, about meat pies in space, about steam on the sun, a star called UI Scooty, and Martin wants to find out more from Fred about his ideas for a science fiction novel. So we'll tackle all of that on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as he does always, every week, without well, he actually fails quite a lot, but we manage to find him and drag him in. It's Professor Fred Watson, astronomer at large. Hello, Fred.
That's because I'm at large, Andrew.
Yes, that's
they're still looking for me.
Yes, that would be it. That would be it.
And I'm very well, thanks, Andrew, and I hope you are too.
Oh, yeah, doing fine. Yeah, just, getting on with it.
In spite of everything.
Yes. Doing what needs to be done, but only if I have to.
That's all right.
That's the life of a retiree, isn't it? You know, I can get around to that in a couple of years.
Yes, you might. You're the classic example of all those people who say, I didn't know what I was going to do in my retirement, but now I don't have time to do anything else.
Yes, I've got a list.
Because of all the things. Yeah, you've got a list too. That's why I'm not retiring, because I don't want to.
I've actually achieved one or two things on the list.
That's good.
Yes, I've taken the bins out now, so that's
very
one.
Good. Yeah.
Done that.
Well done.
Don't have to do that ever again. Or maybe next week. Could be.
No, maybe you do. Yes, you've got a short time horizon there.
Yeah. Yes. Now we've got a fair bit to get through because we're going to dedicate a lot of the program to questions from the global audience today, and we're sort of getting around a bit. But before we do that, let's talk about this amazing day, which was June the 29th, and it was the shortest day in the history of Earth, technically speaking.
It's the shortest day since we've been using atomic clocks to record the time.
I figured, because I got a feeling we used to spin a lot faster than we do now.
We did, that's right. Yeah, probably in the early history of the Earth, it may even have been once every 4 hours. I think that's the theoretical version as to how fast the Earth would have rotated when it was newborn. It's a bit slower than that now, 24 hours. And we're kind of used to the idea of it, of its rotation speed slowing down, because you and I talk about this quite a lot. Yeah. The fact that tidal friction with the moon is causing a transfer of energy from the moon's rotation to from the Earth's rotation to the moon's revolution around the Earth. And what that's doing is slowing the Earth down very, very gradually, but also pushing the moon away very, very gradually. I think it's a bit more than three centimeters per year. So, yeah. A bit more than an inch or thereabouts a year.
Yeah, which doesn't sound much, but over the course of time, it adds up.
That's right. So that's why this story, you might find it a bit surprising. The fact that actually the Earth at the moment is going through a phase where it's actually rotating rather more quickly than it has been. And exactly as you've said, on the 29th of June this year, it set a new record for the shortest day of the atomic clock era. So it was 24 hours minus 1.59 milliseconds. So that's like 23 hours, 59 minutes, 59 point, what is it going to be? 995.
Yes.
Thereabouts, something like that. 94.
Which in simple terms means that if it was your birthday on the 29th of June, you got older just a bit faster than the rest of us.
You did.
No, we all got older faster, basically, but your birthday was shorter than everyone else's. Ha ha.
Well, everybody else who wasn't born on the same day as you. The point here is what's causing it.
Yes.
Andrew. And I mean, as we've said, the long-term increase in the day length, which is about 2 milliseconds per day per century. So every century, the day gets about 2 milliseconds longer. And that's because of the moon's effect on the Earth, the tidal friction effect.
Yep.
But on top of that, there are other factors that cause slowing down and speeding up of the Earth, only by small amounts. A lot of it is to do with the fact that the Earth is actually not a solid body. It's got a liquid core as well as a solid component to the core. It's got this thick mantle on top of the core, which is essentially a liquid rock. It's fairly viscous, but it's still liquid. And on top of that, the crust floats with the continents wandering around on top of the mantle. But all of those things suggest that the Earth is subject to, the sloshing around effects of some of these liquids. And that's before you start adding in the oceans, which themselves have an effect on the Earth's rotation, as does the atmosphere. So atmospheric winds and things of that kind all have an effect. And it's thought that what we're seeing is just a combination of these effects that is actually, over the last 3 years or so, in fact 4 years, it's meant the Earth is actually spinning slightly more quickly generally than it did, with dips every July or June or July thereabouts, which apparently are caused by atmospheric phenomena. And in fact, when you look at the details, you can see that each of the last 4 years has had a particularly short day, lowest point of this graph of how long the day is. Yeah. In 2019, it was July the 16th, and that was almost a millisecond shorter than normal. It was more than that on July the 19th, 2020. It was minus 1.47 milliseconds. On the shortest day in 2021, which was July the 9th, it was 1.46 milliseconds. But this year, on the 29th of June, it was minus 1.59 milliseconds. And so this has led to talk that we might have to introduce the opposite of a leap second, Andrew.
Oh, add one. Or might...
Yeah, well, yes. Well, you subtract one.
Subtract one, yeah, sorry. Because we have been adding leap seconds for a long, long time to keep the clocks on.
That's right, since 1972. And I think there are 27 that have been put in that time, either on the 30th of June or the 31st of December. And what you do is you, at the end of the day, where you're clicking over from 23 hours, 59 minutes, 59 seconds to 0.00000, you actually click over to 60 seconds before you hit zero, and that adds an extra second.
Right.
And that's been done, as I've said, several times. But if you had to take one out, it would be called a drop second, because you drop it rather than leap forward. And that would take you straight from 59 minutes, 58 seconds to 0000 the following day. However, all that is of considerable debate, or the matter of considerable debate, because the IT industry and communications in general hate the idea of leap seconds because it tinkers around with all their computer systems. The computers run on atomic time. These leap seconds are put in to allow universal time, the sort of time as told by the sun, to keep up with atomic time. Yeah. And the danger is that somebody will make a mistake somewhere and an entire, the whole of Facebook will collapse or something of that sort. And it's not impossible because it's actually happened before.
A la the millennium bug.
Yes, it's a bit like the millennium bug, but it happens at these odd times. And so the communications industry is dead set against the idea of leap seconds and reacts with horror at the idea of a drop second, of actually taking a second out. And so I think it may be the case. This has been going on for decades, this argument. But I think might be misreading this, but my reading of what the industry is doing and how things are going, and the scientific community as well, is that in the end the communications people will win, and it will be seen as, better thing to do to ignore the leap seconds and just let solar time drift a little bit away from atomic time. And maybe you could have a leap minute, which you'd need to do every 70 years or so, in order to keep things on track. But it's I think the voices of of reason in the communications industry are shouting louder than the voices of reason in the astronomical and scientific community.
I don't know what they're worried about, Fred. I mean, in the history of humankind, we've never made a mistake.
No, that's right. Never, ever.
I don't know why that's
maybe
brought
just
up
once or
now
twice,
as a potential issue. But I think it's a great story. It makes for really good headlines and a little bit of fun on the radio, which I certainly had today at the expense of everybody born on June 29th. But it's and there's no way of knowing if this phenomenon will continue.
No, that's correct. It is. It's rather unpredictable. There are things that people have pointed to, something called the Chandler Wobble, which itself is a sort of wandering of the pole. The Earth's North Pole wanders around on the icy surface by something like 8 or 9 meters. It's not very much, but that's a sort of periodic phenomenon. And people, it's due to just the mechanics of a rotating body, and in particular one that's not solid. So I think we just got to wait and see, really. We've got to see what the next year brings in June or July, when we can expect this minimum again, and see whether we break the record set in 2022.
Yeah, it'd be interesting. I'm sure someone will be paying attention. It won't be.
No, they will. No doubt you and I will be at the time as well.
I have another theory, Fred. I think it all started on April the 6th, 1938, and I put the blame squarely on Roy J. Plunkett. Roy J. Plunkett caused all of this because he invented Teflon.
There you go.
That's. So I think it's Teflon that's causing the Earth to spin faster.
No, it could be. No friction. There you go.
Slippery devil he is.
Yeah. Next thing you know, the moon will be coming towards us.
Yes. Well, that'll happen next. If we're going faster, it probably will.
Yes.
We'll reel it in. No, it's fascinating.
Reel it in.
Let's get stuck into some questions, Fred. And this first one comes from Doug in Miranda, which is one of the great suburbs of Sydney. And he says, my question is one I've had since I became interested in astronomy, which was only yesterday, way back in my high school days in the 1970s, and is in relation to the Earth's moon. I've noticed that the moon's elevation in the sky varies dramatically throughout each month. Sometimes you see it low in the sky, and then when it's at the same compass point on other days, it can be much higher up and near the zenith. I downloaded a year's worth of data for how high the moon is each day when it circumnavigates, crosses the meridian for my location in Sydney. Now, he said, I'll pause here for Fred to explain that to all of us. We'll just keep going and you can fill in the blank later. From the figures, I can see that the lowest elevation during 2022 is 27.9 degrees from November 13th, or on November 13th, but it climbs to 83.5 degrees on November 26th. That's a variation of 55.6 degrees. I'll take your word for it. Yet the moon's orbit is only inclined by about 5 degrees to the plane of our orbit around the sun. Can you help me understand how this huge difference in elevations is possible when there's such a small deviation in the moon's orbit around Earth? Thanks, and keep up the great work, Doug from Miranda. I love the question. Do you need to explain the meridian first?
Oh, it's just so, yes, in our case, it's when celestial object passes due north. Of course, if you're in the southern hemisphere, it's due south, the meridian. Actually, the meridian goes right across the sky, but, you know, we think of it. In terms of the moon, it's when it's crossing the due north point here in the southern hemisphere.
And if I may ask, there are time meridians as well. Is that a different thing?
Actually, a meridian it's a line of longitude, basically. That's, you know, the way we think of it, but thinking of it on the sky.
So yes, between here and Gunnedah, I think it is, or between, somewhere around there, there's 150-degree meridian, isn't there?
Exactly, that's right. You cross it just this side of, not far this side of Gunnedah. Yeah. Stop there for a cup of tea many times. Yeah. You have to bring your own tea, of course. But,
that's true.
And you think of, so the prime meridian, as it's called, is 0 longitude, and that goes through Greenwich in the south of England. That's called the prime meridian because it's that sort of line of longitude that is essentially 0. So you would have your own meridian there, up there in Dubbo, Andrew, which is a bit further west than 150. It'll be 152 or something.
I'm going to look it up.
53. Check it out. Anyway, the meridian in the sky that Doug means is essentially, the north-south line. So when the moon crosses that north point, that's when he's checked out what its elevation is. And there's a step in the calculation that Doug's missing, which is why he gets the wrong answer. So yes, the moon's orbit is only inclined at 5 degrees to the plane of the Earth's orbit around the sun. But the Earth's orbit around the sun is inclined at 23.5 degrees to the equator.
Right.
Rather the other way around. So it's the equator that's inclined to the plane of the Earth's orbit. So when you do this calculation, so think of first of all about the sun. The sun's height when it crosses the meridian will vary from 23.5 degrees north of the equator to 23.5 degrees south of the equator, which makes 47 degrees difference altogether.
Right.
So its height can vary by 47 degrees. Now, add to that the fact that the moon's orbit is tilted with regard to the Earth's orbit, and you've got another 5 degrees either way, so it's another 10 degrees. So it means that the maximum that you could get of the change in elevation throughout the year would actually be 57 degrees. It's 47 degrees for the inclination of the Earth's orbit and another 10 degrees for the inclination of the moon's orbit to the Earth. So that's a total of 57 degrees, which is staggeringly close to what Doug worked out. He got a variation of 55.6. It just means that we haven't had a situation where all the extremes have come together during that year. But that's the answer. It's a great observation to make. I take my hat off to Doug because he's thought about it and he's worked through it and just missed out one step in the calculation.
Yeah, good job.
Good job.
Honestly, I never thought about it. Never crossed my mind. I never wondered why. So yeah, it's good that he brought it up because it's a natural phenomenon, combination of factors that lead to that variation. So well done, Doug. Got a question without notice, Fred. If you know the answer, just nod. This is from somebody who's listening to our pre-recorded session live or watching perhaps from YouTube. What is Planck heat?
I don't know.
There we go. That was easy.
I would guess the Planck length is the minimum length that can be defined by quantum mechanics. The Planck time is how long it takes you to cross the Planck length, the speed of light. The Planck heat is probably how hot you get when you do that. Yeah. I'd have to look it up. I don't know the answer.
Okay, fair enough. All right. We
dealt with it well. Before.
And the usual answer for everybody who sends us questions, we don't know.
Not quite true, but
no, not quite. Well, in my case, yes, but in Fred's case, no, not quite true. We'll take a little break and be back soon with more questions. You are listening to or watching Space Nuts with Andrew Dunkley and Professor Fred Watson. Let me tell you a little bit about our sponsor, NordVPN. Now, I'm going to do this as I speak. So if I put the URL nordvpn.com/spacenuts into my search engine or into my browser and press enter, it will bring up a special offer for you as a Space Nuts listener. And it's an exclusive cybersecurity package that comes with all the other bells and whistles that NordVPN offers. Now, they've got great credentials. They've been highly recognised by some of the big names in media around the world, including BuzzFeed, Forbes, TEDx, Huffington Post, Wired, BBC. You'll see all that on their website. But what they aim to do, first and foremost, and this is what they're famous for, is to protect your online activity. If you're not using VPN, you are leaving yourselves wide open for exploitation, whether that's from a hacker or just from an opportunist, and it can happen anywhere, especially in public Wi-Fi areas. But the deal also gets you so much more at the moment. So if you click on the grab the deal button, which I've just done, and keep in mind there's a 30-day money-back guarantee from NordVPN if you're not happy. Now, they have several plans. They have a 2-year plan, a 1-year plan, or you can go month by month. But I would certainly recommend the 2-year plan because you get so much more bang for your buck. and there are different levels within each of those time frames. You can get the start package, the plus package, or the complete package. So it's up to you which way you go. But the higher you go, the bigger the saving. So 69% saving on the plan that gives you the complete package. So that's your high-speed VPN, protection from malware. You get a tracker and ad blocker, cross-platform password manager. They're really handy because so many passwords that you need these days and it's hard to remember them. This will do it for you. Data breach scanner and 1 terabyte of encrypted cloud storage. So check it out. It is a really great package available to you as a Space Nuts listener. Just put in the URL nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. And then click on the grab the deal button and find the formula that works best for you. But NordVPN, the best in the business, and we're very proud to have them as our sponsor on Space Nuts. Oh, don't forget the code word Space Nuts to secure the deal. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, we continue to answer questions from the audience, but we got one just before the break about what is Planck heat, and you found the answer. It only took you a few seconds.
It did, yeah. So it's to do with the things that I mentioned, actually, the Planck length and the Planck time. The Planck temperature, and the number is 1.416784 times 10 to the 32, which means it's got 32 zeros after it, degrees Kelvin. This is a huge, huge temperature.
Yeah.
And it's the point is that at that temperature, if you had a hot body at that temperature, an object that was heated to that temperature, that the wavelength of the light that would be emitted by thermal radiation is the Planck length. And the Planck length is that smallest length that you can define thanks to quantum mechanics. So there you go. It's a very nice combination of those bits of different bits of Planck there.
Yeah.
And of course, this is a Planck with a C and a K rather than just a K.
Okay. See, I knew you'd
both
figure it out.
CK.
Knew you'd figure it out. And my little piece of homework, Dubbo, where I am, is at 148.6.
Of course, yes. I was going the wrong
meridian,
way.
the longitude. Yeah. So
I was going the wrong way.
So we have to drive about 300k to get to the 150 degree meridian.
That's taking you a degree and a half.
Yeah. Wow.
Actually, a lot of that is going north, though, because you go to Coonabarabra and more or less northwards and then turn east.
Yeah, that's a good point.
So it's probably more like 100k. Coonabarabra to Gunnedah is 100k.
It is.
Yeah.
Okay. Now, let's get into the rest of our questions. And this one comes from Jem in Sydney, I think. Yes. I saw this on social media. I think it popped up on the Space Nuts podcast group. And it was a little bit of a meme. And Jem says there is a pic of a standard Australian meat pie sitting exposed in space in a tray outside the International Space Stations, which got me thinking, if I were to take a frozen pie and place it outside in space, would it be still frozen and cold inside because space is cold, or burning lava hot crisp inside because of exposure to unfiltered sun and UV radiation, etc.? And would it be edible? I need to know. If I can't have a nice hot crispy 4 and 20 and an ice cold VB in space, I ain't going. Jem. You ain't going anyway. There's not enough room up there anymore.
It's an expression that Jem uses there that I'm not familiar with.
What's that?
Andrew? Because I wasn't born in your fair country. I was born somewhere else. What's a 4 and 20?
It's a meat pie. 4 and 20?
Why?
It's a
why
brand.
is it called that?
It's a brand name. Pie. 4 and 20.
Okay, right.
Yes.
It's not 4. Oh, I suppose 4 and 20 blackbirds baked in a pie.
That's probably where the company got its name from. Yeah. 4
and 20. There you go. So
there are several
blackbirds,
but they're more a prefabricated pie. There's another brand called Sargent's that we have in Australia, and there's Mrs. Max. They make meat pies, which are all pre-made in a factory, and you heat them up. But the real meat pies, the real ones, are the ones you get from the bakeries that they make every day. And Dubbo has more than once won the best meat pie in Australia competition.
Yeah, I know the bakery in question. It's very good, well worth a stop if
Indeed
ever
it
you're
is.
passing through Depot.
It's super popular.
Yeah, it is. You can't park. That's the trouble.
No, you've got nowhere to park.
Anyway.
But the question is, what happens to a
when-
meat pie outside of the International Space Station, basically?
Yeah, the answer is depends which side of the space station you poke your meat pie out
I
of.
knew that'd be the answer. So let's move on to the next question.
Yeah.
No, but let's expand on that a bit. Let's knead the pastry on this one.
Well, very nice. Knead the dough. I'm always kneading dough. I'm sure you are too. The meat pie on the side of the spacecraft that's not being illuminated by the sun would indeed actually not just stay frozen. It would get even more frozen than it was before because it's not receiving any radiant heat from the sky. Might feel a bit of heat from the space station itself, but that's because the space station is shiny. That's to protect, to stop heat transfer. Then it's going to stay cold. On the other side, it will start getting heat from the sun, and will sort of warm up quite quickly. A lot depends on the thermal conductivity of the pastry and the 4 and 20 that's inside it, whether they're blackbirds or not. But whether it'll warm right through, I think it's more likely. I mean, first of all, of course, it will lose all its moisture. So it'll be freeze-dried, effectively.
Right.
Even though it's having radiant heat put on it. So, yes, I think you can forget about eating it. I think it will be very distasteful indeed.
I can imagine. So on the dark side of the ISS, rock hard, cold, and just basically a satellite. And on the shiny side, maybe to warm up a bit, but dry as toast.
Yes, dry.
Okay,
drier than toast.
Drier than toast. I don't know. I've had some pretty dry toast in my time.
Yeah, I think I have too.
But totally inedible, which is. Yeah, not what you want with a meat pie or a pasty or a sausage roll or anything along those lines. Thanks, Jen. Let's go to Bret in Pennsylvania, USA. I like this question. This is Bret from Pennsylvania here. I recently came across an article on Stanford EDU. The article is dated a bit, but the findings from the study puzzled me greatly. The team claims that they found evidence of water in the form of steam on the sun within sunspots. This makes little sense to me, as even within the coldest sunspots, I figure it still has to be too hot for this to occur. I believe the findings were discovered through spectroscopy, which I had done the other day. But I'm sure Fred can make a lot more sense of this. So how is this possible, and is it indeed true? And we were sent a link explaining the findings. So steam in sunspots, possible?
Apparently so. So what holds molecules together is their sort of the attraction between their atoms, and basically that's what keeps molecules held together. And so molecules like being cold temperatures in space. I mean, we're talking now about things in the universe, and typically not in star temperatures. However, I do know that cool stars do have molecules near their outer edges. Red giants, for example, have titanium oxide bands in their spectrum. So that's telling you that that is a molecule that survives in their outer atmospheres. And the spectrum of the sun, being a typical star, has single elements in its spectrum: hydrogen, oxygen, sodium, magnesium. All of those things show up as single elements. But I can imagine that in sunspots, even though they're still pretty hot, sunspot has a lower temperature than the photosphere. Photosphere is at about 5,000 Celsius. Sunspots get to be 1,000 or 2,000 degrees cooler than that, which is why they look black against the heat of the sun.
Yeah.
And I can imagine that if you had the right environment there, the right pressures, the molecules of hydrogen and oxygen, commonly known as H2O, could stay together. So this team, quite right in that Bret's right in pointing out this is an old paper, 25 years old, in fact, almost exactly 25 years old, published on July 17th, 1997. So what's happened is scientists have actually synthesized what they expect the spectrum of water to look like, and they've basically observed this phenomenon in the sun itself. So what they've done is they've actually, and in fact, they've not even done that. They've synthesized it in the laboratory. They've actually done measurements in a laboratory of hot water, which we call steam, vaporized water. So I'm prepared to accept that is possible. I would quite like to follow up, though, on more recent research on that, and I will do. I'll have a look online and see what I can find in the research literature about the spectrum of water in sunspots. Okay. It's an interesting idea
because it's well known that there is water in the stars. That's not unusual. That's been well documented, hasn't it?
It's more in the gas clouds, in cold gas clouds, right. Dust clouds. That's where we see most of these molecules. They form actually in open space. If you've got a cloud of gas and dust with all the right elements in it, they will form molecules. The chemicals will react with each other to form molecules. And stars, as I said, some molecules are present in the atmospheres of normal stars. I think it's very intriguing about what might be in the atmosphere of a sunspot, because, of course, the raw materials of water are there, hydrogen and oxygen. They're both present in quite large quantities in the sun's atmosphere. So you might expect that where conditions are right, that could form molecular water.
Interesting.
And actually, just one other comment on that.
Yeah. That
kind of, I suppose, informs it a little bit more. Water is the commonest two-element molecule in the universe. So you find it everywhere.
Well,
so maybe not surprised that you find it in sunspots.
We are finding it everywhere. It's on the moon, it's on Earth, it's on Mars, it's on Enceladus, it's on, what's the other one? The other ice moon? Europa. So we do know it's out there in
Titan,
vast quantities.
Yeah. Ganymede, all of them. Yeah. They've all got water. Very wet universe that we live in.
And if I may draw the bow, water is life.
It is.
Okay, thank you, Bret. Lovely to hear from you. We are going to take another little break, and we'll be back with a couple of more questions here on Space Nuts with Professor Fred Watson and my good self, Andrew Dunkley. He's not good, I'm good. I'm very good.
You're very good, yeah. Very good indeed.
3, 2, 1.
Space Nuts.
Okay, a couple of more questions, Fred, before we wind up this episode of Space Nuts. And this one comes from Tom, who is in Chicago, Illinois. Hello, Dr. Watson and Andrew. I'm fascinated by the largest observed star, UY Scuti. It is said to be 1,700 times the sun's radius and 5 billion times the volume of the sun. Now, my questions... I put an S on that. Did you hear that? My questions are, 1, how far from UY Scuti would Earth need to orbit to be in the habitable zone, similar to its own habitable zone around our sun? 2, how long would it take for the Earth to complete one orbit, or the length of a year? 3, would Earth's orbital speed increase? 4, what are additional changes that we would notice, such as the length of days, sunsets, sunrises, etc.? Thanks for your insights. Love the podcast. All the best, Tom from Chicago. Okay, where do you want to start? At the start?
Yeah, let's start at the start. I don't know the answers to any of these.
Okay, but, well, let's just stop there.
Let's just think about, UY Scuti, with 1,700 times or 1,700 times bigger than the sun in terms of its diameter. So the sun's about 1.3 million kilometers in diameter. So you're talking about roughly 1,700 million kilometers in diameter for more like 2 billion kilometres. Wait a minute, that's all wrong. It can't be that size. I'm doing the calculation wrongly here. Basically 2,000 million kilometres. That sounds ridiculous.
Yeah.
It's the size of the orbit of Saturn. 1.5 billion kilometers. I'm not very good at mental arithmetic, but yeah. So you're talking about the habitable zone being probably about the same as where Neptune is now, or something like that, just hazarding a guess.
Wow.
For this large star, probably even further. How long would it take for the Earth to complete one orbit? About the same as what Neptune does.
Yeah.
What's that, 178 years, if I remember?
That sounds familiar. Let me look it up.
You have a look it up so you can correct me. That would be, and so that's the length of its year. How long it?
165 years.
Oh, there we're not too far off. The length of a year for a planet would be 165 years if it was out at Neptune's orbit. Of course, we've already established that the thing is inside the orbit of the Earth, is inside the star, so we can forget about the Earth's orbit. Would Earth's orbital speed increase? You bet it would. Inside the star, it would do all kinds of weird things. And what are additional changes we'd notice, such as length of day, sunsets, sunrises, etc.? That's a fairly frivolous answer to what is clearly a serious question, Tom. And I'd really need to go to the books and look it all up. But you can tell from that a star so much bigger than the sun has a profound effect on its neighborhood, and it is actually going to essentially put you in a totally different regime from what we find in the solar system. A star that big and with that sort of mass is also likely to be very hot. It will also likely radiate, you probably get lots of ultraviolet, but you also get flares on its surface, which is what sends out all these subatomic particles to the environment that it's in and is not good for living organisms. So all of those, the details that you ask about, I think would be put into a different context when you're thinking about such a different star from what the sun is.
Life as we know it could not exist there, is what you're saying.
That might be the bottom line.
Yeah.
It's life, Jim, but not...
Last week we talked about our sun not being the best possible candidate for our planet to orbit, but this one, UY Scooty, definitely is not a preference to where we are now.
No, it's not. Yes, that's right. We did talk about more desirable stars to orbit around, but this is not one of them.
Yes, indeed. All right. Yeah, so substantial changes is the answer. Tom, living out near Neptune, that's a long way from everywhere. But
it's just like being in Australia, really.
Yeah, it is a bit. We're a long way from everywhere here. Now, one final question before we wrap it up this week, and it's an audio question from our second favourite science fiction novelist.
Yes.
And that is Martin from Potomac in the United States.
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres, with a question for my latest science fiction novel project that I'm working on about a starship launched by an obnoxious billionaire named Eric Rusk. Quite unlikely, I know. So the idea is it's a hollowed-out asteroid. It's got a fusion engine, and it's going to gather fuel in interstellar space with a buzzard ramjet. It's going to accelerate at 1G until it reaches a cruising speed close to c, the speed of light, and then decelerate so it can get to its destination in the TRAPPIST system, which has Earth-like planets in it. So my questions are, how much turnaround time would be reasonable for building up to 1G acceleration, for cruising speed, and for slowing down deceleration of 1G? And also, how much time dilation will they experience? Like, how many years will have passed for them over the time that it takes the ship to travel the almost 40 light years to TRAPPIST? Love your show, guys. Hope you take my question. Thanks. Bye. Oh, and I'm in Potomac, Maryland, USA.
I already knew that. Thank you, Martin. Great to hear from you, and mesmerised by your capacity to churn out sci-fi novels. It's fantastic. So he's what was the name of the character? Rusk. Yeah, that's got a familiar ring to it.
I wasn't going to go there.
Neither am
Eric
I.
Rusk. Eric Rusk. I don't
Eric
know.
Rusk.
Doesn't ring any bells at all.
Now, so a couple of questions within that concept. The turnaround time for acceleration, cruise speed, and deceleration to get to TRAPPIST from Earth. How do you calculate the allowances? This is accelerating to 1G and then whatever.
Well, yeah, the acceleration to 1G takes you about half a minute, or less than that. So that, just you can ignore that part of the equation. And if you want to travel at a constant acceleration of 1G, then it's very easy to calculate how long it will take you to reach almost the speed of light, because what you have is the famous equation V equals AT. V is the velocity, A is the acceleration, and T is how long you do it for. So 1G is, 9.5 meters per second squared. The acceleration, that's the acceleration. The velocity you want to achieve is 300. It's actually 300 million meters per second. So if you divide 300 million by 10, effectively, that's the acceleration is for 1G. Yeah. You've got essentially 30 million. That's seconds. So you divide that by 60 to get it into minutes, and 24 to get it into days. And you'll get a number that'll tell you how long it will take you to get to the speed of light with the 1G acceleration. It's not all that long, actually. Wait a minute, 30 million seconds. Oh, yeah, it is. It's quite a long time. But you can also work out, if you go into the TRAPPIST system, I can't remember its distance. Was it 50 light years? Something like
40,
that.
40, wasn't it? I don't know.
40, yeah. You need to work that out as well so that you don't find that the acceleration is taking you too long. My guess is it's not. I think you're going to have quite a nice time
21
getting there.
years to reach light speed.
21 years to reach light speed. There you go.
Yeah.
Thank you, Andrew. Thank you. That's a nice thing to remember, that 30 million seconds, you would pass that mark at the age of 21.
That's assuming I did it right.
Yeah, assuming you did it right. Well, I hope you have done. I'm sure you have.
No, probably
as well.
not.
I'm too busy talking to you. Anyway, I think any science fiction writer worth their salt ought to be able to calculate these things. So get on with it, Martin.
Yeah. Or just make it up like I do.
I'll make it up like Andrew does. I was going to say, Andrew has never come to me with a question like that, so I assume everything in your books is totally made
just
up.
Rubbish.
Rubbish, yes. No, it's great stuff. I love the idea of traveling towards the speed of light and doing it in style.
Yes, indeed. Yeah. I've heard theories about long-haul interstellar travel, and they reckon it'll be like a generational type of thing, with potential for the technology we could create. If we ever did embark on a journey like that, you'd probably have to have a few generations of people live their lives certainly in space before they reach their destination.
Yeah, certainly in terms of conventional rocket travel, it's, if you imagine New Horizons heading off to Proxima Centauri rather than Pluto at the speed that it set off at, it will be 60 to 100,000 years before it got there. So you're talking about not just generations, you're talking about mega generations. So you've got to find a way of accelerating spacecraft to higher speeds than that if you're going to make any sense of interstellar travel. And actually, it's a nice idea to have a spacecraft continuously accelerating at 1G, because you've provided yourself with an environment that's exactly what we've got on Earth, at least gravitationally. Yeah. Acceleration and gravity being equivalent, as Einstein noted in 1907. What your problem is the energy to do that. That's where it gets tricky, which is why we're thinking about light sails and things of that sort.
Yes. Well, to reach light speed, didn't we say that you'd have to use more than the energy that exists in the universe? Was that it?
Oh, that's right. So you never get to the speed of light because you need infinite energy.
Yes. So just make it up, Martin.
Make it up, yeah.
Just pretend. Yeah. No, great question, though. Thanks for sending it in. Lovely to hear from you again. That's where we're going to wrap it up, Fred. And, of course, we're actually a bit short of questions at the moment, so please jump on our website and send us some questions. We've got a few stragglers that we haven't got to yet, but the barrel is basically empty. So if you say, hang on a minute, I sent in questions you haven't answered, chances are we answered them for someone else. So it's not like we ignored you. We don't ignore anybody. We read and listen to them all. But sometimes people ask the same questions as someone else. So we only answer one of them.
The week after we've asked. After we've answered.
Yeah, a couple of we answered last week came up this week. Yeah. So it's funny how that happens. But yes, go to our website, spacenuts.podcast.com or spacenuts.io. You can ask questions via the AMA tab or the send us your audio question button on the right-hand side. Would love to hear from you. In the meantime, please keep the reviews coming through on your favourite podcast platform, whether that is YouTube or iHeartRadio or Google Podcasts or Apple Podcasts or wherever you listen to us. Please leave us your reviews. They are greatly appreciated and they help grow the family. Don't forget social media. We're everywhere there. And you can talk to each other through the Facebook podcast group. Space Nuts podcast group on Facebook is what I'm trying to say, because that's where you can meet each other and chat to each other and share your photos of things you've seen in space from your own backyard. It's a really great group and ever growing. Fred, thanks so much. Great to have you with us yet again. Thanks for answering all those questions.
It's a pleasure. I've just remembered a couple of Martins that we didn't get to about time dilation, but never mind. She'll be right.
We'll do time dilation another day.
Yeah, you'll certainly have it. You'll have your time dilation.
Yes. Well, that's because we would have answered it, except there was a time dilation issue.
Yeah. In fact, there was with your recording last week, wasn't there?
It was a terrible time last week.
Yeah.
That's the way it goes sometimes. All right, Fred, thanks very much. We'll catch you next time.
Sounds great. Thanks, Andrew. Take care.
Professor Fred Watson, astronomer at large, with me every week here on Space Nuts. And thanks to Hugh in the studio for getting another couple of packets of blue tack to put it all together. And next week, we'll be back again with another edition of Space Nuts. We'll talk to you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Thanks for watching or listening. If you're part of our live audience, we'll see you again next week. I'm going to hit the stop button, which means we'll disappear. Uru.